Hi all. In this video we will derive the Einstein relation. So our goal is to find a relationship between the diffusion coefficient d and the fluid friction coefficient zeta. So we will start off where we have left off previously. So we have a 1D random walk, and so we'll start at some point and we can go to another point, either forward or backwards, and the spacing here is L, and a step occurs every tau. So the spacing is L, and the step occurs every tau. So that means that our velocity u will be either plus or minus, because we're either going forward or backward, L over tau. This is the velocity between collisions. Now we can ask what happens if there's a constant force applied to this. So we can ask, what the um, position of the particle, how it varies in time. So we can use a kinematic equation to solve that. So we're going to have a constant force F, and that's going to be the only force acting on it. We're going to assume that this force is so much bigger than any other force, so gravity or whatever. So the acceleration of this will just be equal to F over m. And we can say that at a later time, so t plus tau, and the x of t. So this is just the change in position will be equal to u times tau plus a times 1/2, so it's going to be f over 2m times tau squared. This is the change in position in a time tau. So we have gone a time tau, and this is the amount of position changing due to the velocity, and this is due to the acceleration. So if we now take an average of this, so we take an average of both sides, we'll get the average of this side. It's going to be equal to the average of u times tau. So tau is a constant, so we can pull it out. All of this, the f, the 2, the m, the tau squared, those are all constant, so they just get added on because they never change in time. And we need to remember that since it's equally likely that it steps forward or backward, this u on average will be equal to 0. Because if it's equally likely to step forward or backward, then it's on average the velocity will be 0. So now we're just left with x of t plus tau minus x of t equal to f over 2m tau squared. So what we can do is we can divide this side by tau and also this side over here. So now we're left with f over 2m times tau is equal to the change in position over time, and we'll just define this here as the drift velocity. And if you remember from Module 2, we found that a particle moving through a viscous fluid, the terminal velocity v would be equal to 1 over zeta times the force applied on it. So what we can see here is that zeta is just going to be equal to 2m over tau. So this is a good intermediate step. This is something that we wanted to find, and we're going to be using it in a second, because what we really want to do is relate the diffusion coefficient and zeta. So we found something for zeta that we can relate to in our little microscopic random walk model. So we're going to recall some results. So what we just found was that zeta equals 2m over tau. Previously, in this module, we found that the diffusion coefficient is equal to the length squared over 2 times tau, and that the average of the velocities squared is equal to the length squared over tau squared. So what we're going to do now is multiply d times zeta, and that's going to be 2m over tau times L squared over 2 tau, and now we'll end up getting m L squared over tau squared, and that right here is just our average, the average of our squared velocity. So we can just rewrite this as this. Now the last thing that we need to remember is in the module 3, we quoted a result that we'll prove in module 10, which is that 1/2 m, the average of the squared velocity, is equal to 1/2 kbt, or that m, the average of the squared velocity, is equal to kbt. So we can just substitute that in here. So we'll get d zeta equals kbt, and then our diffusion coefficient d is going to be equal to kbt over zeta. And this right here is the Einstein relationship. So this is important for a few different reasons, but it also has a few consequences. So what this is saying is that the diffusion of a particle or a system of particles is going to be linearly proportional to the temperature. So if you increase the temperature, then the particles will diffuse faster, but if you decrease the temperature, particles will diffuse slower. It's inversely proportional to this frictional coefficient. And what's really neat about this is what we can do is we can solve for Boltzmann's constant. So it's d times zeta over t. And Boltzmann constant is a constant, so all of these numbers, which can be measured independently, so the fluid friction can be measured independently of the diffusion, and the temperature can be measured independently of all of those. But if you put them all together, so a particle in some fluid and it's going to diffuse, then you can accurately measure the Boltzmann constant, which is pretty neat. All right, thank you very much.